Video on solving exponential equations, which we saw yesterday, solving exponential equations. The difference between yesterday's and today's equations is what's going on in the exponent. And yesterday we saw lots of fractions in the exponent. We learned to use the reciprocal of that fractional exponent in order to solve the equation. Today what we're going to see is we're going to see the variable in the exponent. We actually had one like this on an earlier homework assignment, and a lot of you seemed to have no problem with it. If you take a look at this expression here, an equal sign means that whatever's on the left is the same as what's on the right. Well, if we've got 2 to the third on the left and we've got 2 to the z on the right, that means that z has to be the equivalent of a 3. So what are we really doing there? We're saying as long as we have the same base, we can set those two exponents equal. And in this case, it's as simple as that because it's already solved for z. And that's the idea of any equation, is to solve it for the variable. Well, you don't always see the same bases. If you take a look at this example here, 3 squared equals 81 to the x. We don't have the same bases, but suppose we did. Suppose that I could rewrite 81 as something with a base of 3, which is exactly what I'm going to do to solve this problem. I'm going to leave this as 3 squared, and I'm going to change 81 into something else. Now notice that everything else has been brought down exactly the way it was. The only thing I'll be changing going from line 1 to line 2 is the 81. And I'm going to change 81 to try to match this base. Well, I can rewrite 81 as 3 to the 4th power. When you take a look at that expression there, if we clean it up, we get, and it's not difficult to do, oops, I'll try using something else. 3 squared is equal to, well, our laws of exponents say when you have that parentheses, 2 exponents out here, you just multiply. So it says 3 squared is equal to 3 to the 4x. And now we're looking at something very similar to the first one where we have the same base. They're equal, so that means they're equivalent. So if the bases are the same, that means the exponents have to be the same. So I'll set 2 equal to 4x. We'll solve it by dividing both sides by 4, and this will tell me that x is equal to 1/2, and that'll be my answer. And you can certainly use your calculator to check that. You can store 1/2 into x, and you can type this expression, and it'll say that's true. Not always quite that simple. When you see a base of 5 here and you see this 5 in the denominator, or something having to do with 5 in the denominator, well, that's telling you that you've got this negative exponent that you can start working with. All right, so let's take care of negative exponents first. Let's take care of moving anything that might be added or subtracted first. A shortcut method of getting rid of that -2 when you have a fraction inside the parentheses is to turn that fraction over. When I turn 1/5 over, it's just plain old 5. I don't have to write that denominator, but that made my exponent positive, just taking the reciprocal of that fraction. On the other side, I still have 5 to the y, and now we have the same base. In order for this to be a true statement, in order for that equals to be legitimate, that means that if the bases are the same, the exponents have to be the same, and I've just solved for y. Again, you can check that with using your Inspire just by storing. Another example here. Again, looking for the same base. I'm in search of the same base. The question is, look at the smaller base. We'll leave that alone. We'll say, can we write 8 as 2 to some power? And you can. I'm going to bring everything else down exactly the way it was. And I'm going to change that 8 to 2 to the 3rd. When I rewrite this, 2 to the 6th is equal to 2 to the 2x plus 2. I will take those two exponents, the 6 and the 2x plus 2, I'll set them equal to each other, and it'll be some pretty straightforward algebra from there. I'll leave that one for you to solve. This last one down here on this page, well, we can look at that base of 8. That is a smaller base. We always want to start by looking at the smaller base and saying, can I write 16 as 8 to some power? Well, that's not going to work for me. 8 to the 1st is 8. 8 to the 2nd is 64. That means that I need to go even smaller than 8. So let's think about other numbers we can rewrite 8 with. If you're thinking of exponents, you can change 8 to 2 to the 3rd. So that's what I'm going to do. I'm going to make that replacement. 8 has become 2 to the 3rd, but everything else I'm going to bring down, well, at least on this side, everything else I'm going to bring down the way it is. The only change here is that 8 has been changed to 2 to the 3rd. Now my question is there any way to write 16 as a base of 2? And as a matter of fact, we can change 16 to 2 to the 4th power. Again, leaving the exponent the way it was. So now if you look at this expression, you see two bases that are the same. Let's first clean up the expression. It becomes 2 to the 4x minus, well, if you're multiplying this 4 times this binomial, you have to distribute that 4. So it becomes 4x minus 4 is equal to 2 to 3x. And now you can see that you have an equation. These two exponents have to be equal, so 4x minus 4 is equal to 3x. Some simple algebra to solve here. We'll subtract 3x from both sides and add 4 to both sides. It's going to give me x is equal to 4. And again, you can plug that, store that 4 in your Inspire, type this expression, it should say true. Remember, if you're going to be using the Inspire to check answers, generally the true and the false work, but if you're working with irrational numbers, which includes trig functions, you probably want to just get a value for this side, get a different value for the, get a separate value for this side, and make sure those two values are equal. And then the rounding, you'll see that they are equal. Two more examples for you here. I've got 9 to the x minus 1 equals 27 to the x. Well, again, we're in search of like bases. If I rewrite 9 as 3 squared, that'll allow me to change that base. Bring down the x minus 1, no reason to change that. Bring down the equals, no reason to change that. Let's rewrite 27 as 3 to the third, and bring down that exponent of x. That will yield the following equation. Again, don't forget to distribute that. I get 2x minus 2 is equal to 3x. What am I doing there? I'm just setting those two exponents equal. That's a multiplication. That's a multiplication. That's what gives rise to my equation that I'll solve here. When I solve it, I'm going to subtract 2x from both sides. That'll leave me a negative 2 is equal to x, and I'll be done with that problem. On the final problem for today's lesson, you'll notice a base of 4 down here, base of 8 there. Well, again, we want to change this problem into like bases. So let me start off by changing the 4 to 2 squared. And I'm going to leave everything else on the left-hand side the way it is for now. And on the right-hand side, we'll change an 8 to a 2 to the third. And we'll bring down that 1 minus x. Okay, well, we need a base of 2, and we have a common base of 2, but this base is in the denominator. So the question is, how can we change that to a base of 2 in the numerator? Well, that's as simple as changing that positive 2 exponent to a negative 2. I can rewrite this expression. I can move that 2 squared to the top of the fraction. When I move it to the top of the fraction, I change the sign on the exponent. So now it's 2 to the minus 2 times x is equal to 2 to the third times 1 minus x, and I'll use that to write my equation and solve it. My equation is going to be negative 2x is equal to, again distributing here, 3 minus 3x. We'll solve that, add 2x, let me add 3x to both sides. And that will leave me with an x is equal to 3. And again, we can store that and check it for our answer. So as long as you can find a same base, then there's no problem solving these. It's sometimes a little bit more work than others. You might have to apply your rules of exponents. In this last case, we had to apply our rules about what to do with a negative exponent, or how to get that negative exponent.